In this example, we would like to continue our study of the law of conservation of energy. You might remember that in the last example we set up the problem. We have a particle moving in space from one point A to another point B, and the particle is taking any path, C, from A to B. This path is parametrized by a vector function. We may or may not need that in this conversation, but we have it, of course, if we need it. And what we showed in the last video was that the work done, by the way, there's a vector field defined here as well. So there's a vector field acting on our particle at every point here. And in the last video we showed that the work done by this vector field on this moving particle is equal to the difference in the kinetic energy from the terminal point to the initial point. So the change in kinetic energy, that's equal to the work done by the vector field on the particle as it moves along this path. So in this video we would like to make another assumption, add an assumption here, and see what happens. So for this video, let's suppose that our vector field F is conservative. Conservative vector fields, remember, are vector fields who could be realized or can be realized as the gradient field of some function, and that function is called a potential function for the vector field. And so let's say that this vector field F has lowercase f as a potential function. So let's let lowercase f be a potential function for big F. Now, it turns out that in physics the potential function is, closely related to the vector field, but the potential function in some ways has the wrong sign. And so in physics we define, this is a definition now, okay? We define the potential energy of a particle that's moving in this vector field. So I'm just going to call this, we define the potential energy. I won't write down everything here, but this is a potential energy of the particle moving in the field to be, this is a function, we'll call it P for potential energy, but it's going to be equal to the opposite of the potential function. So P is equal to minus F, and therefore what we get, right, so therefore capital F as a vector field is equal to the negative of the gradient of the potential energy, okay, of any particle moving in this field. And so these are our assumptions. Let's now try to compute the work done where we regard F in this light. And remember, this assumption that F is conservative is an extra assumption that we didn't have when we computed this formula up here. Okay, so let's check it. We want to compute the work, right? The work is the integral along the curve or the path C of f dot dr. But we know that since f is conservative, that f is given by the gradient of this function minus p, or the minus sign can come out of the gradient. That's what I did here. And so this is equal to the negative of the path integral along C of the gradient of p dot dr. All right, and at this point, so in the last example, we had to do some work to, no pun intended, we had to do some work to compute the integral to show that the kinetic energy was the antiderivative of the f dot dr, right? In this case, though, we can just invoke the fundamental theorem of path integrals, which says that if we integrate a gradient field, right, then the values of the integral are just evaluating the potential function at the endpoints. So this one we don't have to write down as much, but we put in the work, again, no pun intended, when we prove the fundamental theorem of path integrals. So this is why you always prove your theorems, so that you don't have to ever question whether or not they apply. So the fundamental theorem of path integrals then tells us, we've still got this minus sign here, right? But it tells us that the path integral itself is equal to the value of P of B minus P of A. All right, but the minus sign here is going to flip everything, and what we end up with is that the work done in terms of the potential energy is equal to, so the work done by the vector field on the particle is equal to the difference in the potential energy still, but it's P of A minus P of B. Okay, now let's put this all together. We've got a formula for the work in terms of kinetic energy, the difference in the kinetic energy, K of B minus K of A. We just worked out a formula in terms of potential energy when our vector field is conservative. And so when our vector field is conservative, or our force field is conservative, then these two must be equal, because they're both equal, they're different representations of the work done by the vector field on the particle. And here's what we learn. All right, so when F, our vector field F, is conservative, all right, then along some curve C that connects A to B, again, the curve itself doesn't matter, it's just the endpoints, I have way too many commas here, but that's okay. On one hand, we computed that K of B minus K of A was equal to the work, right? This is all equal to the work. On the other hand, we just computed that this same work is equal to the difference in the potential energy. And if we rearrange this by adding the K of A to both sides and adding the P of B to both sides, what we end up with is the following. I'm going to move the A's to the right-hand side, the left-hand side, sorry. The P of A plus K of A is equal to P of B plus K of B. All right, and so this says that the sum of the potential and kinetic energy at point A is the same as the sum of the potential energy and kinetic energy at point B. All right, and so in other words, no energy is lost. And that's exactly what the law of conservation of energy says. Okay, and so this is a calculus proof of the law, or a calculus derivation, you could argue, of the law of conservation